the car hits 0 for final velocity, it's at 3.29 seconds.
Okay.
I know that.
So V equals 0 at 3.29 seconds. Okay.
And then so I knew how to find the displacement at traveling for the first 6 seconds, what is the car's displacement, but I didn't know how to find the distance traveled. The displacement was 63.58 meters. No, I lied, 12 meters.
So displacement is 63.58?
No. The displacement is 12 meters at 6 seconds. My question is, how do I find out the distance traveled?
All right, we know that it stopped.
Mm-hmm.
The final velocity is 23 plus -7 times 6. That's 42, -19 meters per second. Unless I made a Carol's error.
Okay.
So, given that the initial velocity is positive 23 meters per second, the final velocity is negative 19 meters per second, and also the idea that it stops at some point, what do we know about the beginning of the trip and the end of the trip as far as the car goes? Yeah, it does turn around. So, just for the sake of the diagram, I'm going to assume that to the right is positive. So it starts out heading this way, it stops at 3.29 seconds, and then it turns around. I know it's going to end up on the positive side because my overall displacement is 12 meters. So it's going to end up 12 meters from where I started. So this is basically an attempt at a diagram of what the path is. The distance would be how far it takes to get to here plus how far it takes to get back.
So we need to figure out the displacement at about 3.29 seconds.
Yep.
Times that by 2 and subtract 12.
And to find that right there, since we know time, we could use the delta S equals VIT plus 1/2 AT squared. Or we know initial and final velocities for this segment right here. So we could also use the average velocity times time. The displacement VI plus VF over 2 times time. So that's going to be 23 plus 0 over 2 times 3.29, which is some number. Let's see, so 11, 33, somewhere around 34. I think
37.835
37.835
meters, yeah.
So it goes on 37, almost 38 meters in the positive direction, it turns around, comes back, ends up 12 meters from where he started. So there are more complicated ways of doing the next bit, but I know the distance from here to here is 37.835 meters. From here to here is 12 meters, so I can calculate that just by subtracting 25.835 meters. And so the distance traveled would be the 37.8 plus the 25.8. So the distance here, the distance back, and so you would add those together and get something presumably magical. Is that different from what I've written down?
It's 0.1 difference, but it's not
Okay.
that big of a deal. Okay, so can you tell me what time is the car's displacement negative 90 meters?
Negative 90 meters? Is that what you said?
Yeah.
All right, so assuming, and I assume I did, I assumed this when I wrote that if the problem could potentially keep going. So we know he's heading back this way, and so the question is, at what time does he hit negative 90?
Yes.
I don't know what the final velocity is anymore, but I still know the initial velocity, I know the displacement, I know acceleration. I know three things, and I'm trying to find time. I'm gonna use the classic delta S equals VIT plus 1/2 AT squared. And so I have negative 90 is equal to 23t plus 1/2 negative 7 t squared, quadratic equation. I can use quadratic formula. So I have 3.5 t squared minus 23t minus 90 equals 0. I am going to get two answers. One will be a positive time, one will be a negative time. The positive time is the correct answer.
Okay. And then, my last question is, if we're given a graph that's velocity versus time graph, how can I sketch the displacement versus time graph? Because I know how to get like the acceleration, but I don't know how to sketch the displacement versus time.
It is tougher that way. All right. Was that a curve I gave you, or a straight line? What did I give you?
It was a straight line, so.
They gave you a straight line?
No, it was a curve. Okay, there's two questions. There's one with a straight line and another test that has a curve. But this is the one that I have pulled up. So there's two of them. Not from this test, but another test.
Another test. Do you want me to do the straight line one? Well, I can do both.
We can make
Sorry, guys.
All right. If my velocity is straight, one way of looking at this is the slope of my displacement time graph, or the slope of my position time graph. It's either.
Yeah.
Both. But the only difference between displacement versus time and position versus time is shifting up or down. Doesn't squish this way, it just shifts up and down, so the slopes will be the same.
Can you say that again?
My position time graph, so if I have a position time graph that looks like that, that's position time. That's my starting point. My displacement time would look almost identical, except it would start here. So those curves are supposed to look the same. The only difference is the position is relative to the origin, displacement is relative to the starting point. Or I could so I know that since my velocity is low here, then my slope will be small. I know my slope is 0 here, my velocity is 0, so my slope of displacement time is 0. So just doing a first draft crude sketch, velocity is 0, slope is 0, my slope is negative, my slope becomes positive, so it would do something like that. My slope increases, my velocity increases as I go, so my slope of displacement time should increase as I go. Another way of looking at it, for those who've had some calculus, if this is a first order polynomial, then this displacement will be a second order polynomial, in other words, a parabola. If this were a parabola, this would be a third order polynomial. So the crude sketch here of, we'll worry about how much we need to shift it, but we start out, we have a negative slope, we have a 0 slope, and then we have an increasing positive slope. So negative slope, 0 slope, increasing positive slope. Now, the question is, what's the starting point? Does starting point mean that time is equal to 0? Well, if so, then if that is my starting point right there, when time is equal to 0, then I need to draw this so that my displacement goes through the origin here. So I would shift up the graph. Now, I can't remember my reasoning at that point, because I started it from negative time to something, so you could make the argument that the starting point is that negative time.
So based off of this starting time, that's what's shifting, like, where the
Yeah.
parabola hits.
The displacement should be at 0 at the starting time.
Oh, so it would be like, for example, here it starts at -3 seconds. So that means it would be 0 at -3.
Yeah, I think I would have to accept either that, I would have to accept that, or if you interpret it as the starting point was at time is equal to 0, I would go either way.
Okay, and then,
And if it's curved,
and if it's curved, yeah.
before we were talking about displacement versus time, given velocity. If I think about the area here, I have an area, so my displacement at that point would be whatever that area is. My area is not increasing linearly, or the area is increasing linearly. I think I can safely say it's not linear, because that's my area to start with. If I do the same time segment, well, this total area is more than double that. So this is not a straight line. So the area under the curve is increasing faster than time is. So again, parabola. That was a horrible explanation, but I'm going to stick with it for now. If I have a curve, something like that.
Oh, yes.
I'm starting out, so if I have zeros, I have a positive slope here.
Yeah.
I always have to go back, after I've done it, I have to shoot back just to make sure I didn't get something backwards like I just spoke. My velocity is positive the entire time.
Okay.
So my slope of my position or displacement graph needs to be positive the entire time. From here onwards. It is a higher velocity here than here, so my slope will be steeper here than here. Matter of fact, this will be for time greater than 0, my lowest positive slope will be around this time right here.
Okay.
Because my velocity is higher here than here, I'm traveling greater distance in the same amount of time than I am here. So I would sort of start out with increasing slope. Let's see, do I want to go that way? No. The velocity is increasing, so no, that was right. And then my velocity, too steep. My velocity decreases, and then increases again. And then I would think through it. So smallest velocity in the positive region, so that should be the smallest slope. That's roughly the same right there, so my slope is roughly the same here as here. It should not be. Yeah. My velocity is increasing, so this would increase more. Velocity is still increasing. Something like that.
So why, when there's a peak, we're not showing that it's changing direction? Like, is it like subtly changing direction?
This,
Yeah.
it's not changing direction, it's just, it's traveling quickly and then slowing down and then traveling quickly. traveling in the same direction the entire time after.
Oh, okay.
It's only traveling in the reverse direction. It switches directions at this time right here.
Okay.
So that's when I would have, you know, a bottom, a trough would be at that point.
Yeah. Yeah, okay. That makes sense.
These given velocity, trying to find displacement given velocity, it's not. I don't think it's obvious. Given a position or displacement graph, finding velocity, that's just slope. That's far simpler than doing this. But it just takes a couple iterations just to, so I do this and then I look back and say, all right, if I created a velocity time graph from this, what would it look like? If it looks like that, nailed it. If it doesn't look like that, make adjustments.
Or multiply it by that. Oh, yeah, because you didn't have the dash.
Okay.
Other questions?
So this is both velocity versus time. What is the bottom one?
That's velocity time, this is displacement time or position time. Now it's a matter of shifting it to match either position or displacement.
You get to pick your own.
All right. Any other questions? Okay. The last thing we did the double ramp, no friction. Is that right?